This video demonstrates the fatigue analysis using ANSYS Workbench. The model considered over here is an automotive component. Here, the body is made up of structural steel, is having two bolting locations at the top as well as the bottom. An extended lateral arm is experiencing a force of magnitude 200 newtons, which is a cyclic loading or fatigue loading. The member is supported by a supporting rib to add the strength. The objective of this analysis is to evaluate the fatigue failure or to evaluate the number of cycles this particular part is going to experience before it fails. Before we proceed with the complete steps involved in the analysis or the fatigue failure analysis, let us look into what are the different types of fatigue analysis and how we need to approach and what results need to be evaluated for the analysis of any part. The methods of fatigue analysis. The first method is stress life fatigue analysis, which means the total life of the part can be predicted in this. The second is the strain life, which means the crack initiation only can be predicted in this. The third is the fracture mechanics, that is, the crack life can be evaluated. The fatigue life or the total life is the summation of crack initiation plus the crack life. The fatigue analysis can be further classified into two main categories: high cycle fatigue called as HCF and low cycle fatigue LCF. If body is experiencing the number of cycles which is greater than 10 raised to 5, then it is a high cycle fatigue. If the member is experiencing the number of cycles less than 10 raised to 5, we call it as low cycle fatigue. Here we have the alternating stress versus the number of cycles, tabular data for the structural steel. This table indicates that if the alternating stress observed on the structural steel member, I repeat, if the alternating stress which is observed on the structural steel member is 4000 MPa, then that part will survive for only 10 number of cycles. When the stress life reduces, the number of cycles increases. The same way for 441 MPa stress, the number of cycles is 2000, and if the part or the member is designed to experience the stress of only 86.2 MPa, then that part is going to last for 10 raised to 6 cycles. We call it as infinite number of cycles, which means any part which crosses 10 raised to 6 cycles will reach to the infinite number of cycles. Right side shown is the graph of the fatigue or the SN curve for the structural steel. We can observe here, as the stress increases, the corresponding cycles are less. As the stress go on decreasing, the number of cycles will go on increasing for that member. Having understood about the fatigue analysis methods and the fatigue data for the structural steel, let us proceed to what output that need to be evaluated for the fatigue analysis. The first is fatigue life. Fatigue life is the available life for the given fatigue analysis. The fatigue life can be over a whole model, or it can be on the parts of the assembly, or it can be on the surfaces or edges or vertices of any part. If we load the body and the load is of constant amplitude, this represents the number of cycles until the part will fail due to the fatigue. If the loading is not constant, this represents number of loading blocks until the failure. In actual, for an example, consider the fatigue life for a body was found to be 24,000 cycles. And we are loading the body for 1 hour every day. Then the expected model life would be 1000 days. Next is fatigue damage. Fatigue damage is defined as the design life divided by the available life. The default design life can be set manually in ANSYS Workbench. By default, it is 10:6. For fatigue damage, values greater than 1 indicates the failure of the body before the design life is reached. Next is fatigue safety factor. It is a factor of safety with respect to a fatigue failure at given design life. The maximum factor of safety is 15. For fatigue safety factor, values less than 1 indicates that the failure happened before the design life is reached. Next is fatigue sensitivity. It shows how the fatigue results change as a function of loading at critical locations on the body. Sensitivity may be found for life, for damage, or factor of safety. The user may set number of points as the load variation limits. For example, user may wish to see the sensitivity of the model's life if the body is loaded 50% with respect to current loading or 150% with respect to the current loading. That means 0.5 times the current load applied or 1.5 times the load is applied. Next is biaxiality indication. This biaxiality indication results gives user some idea of stress state over the whole model and how to interpret the results. The real world stress states are usually multi-axial. Biaxiality indication is defined as the principal stress smaller in magnitude divided by larger principal stress and ignoring the principal stress which is near to zero. A biaxiality of 0 corresponds to uniaxial stress. A value of -1 corresponds to pure shear and the value of 1 corresponds to the pure biaxial state. All these results we are going to evaluate in this analysis. Let us begin with the tutorial. Create a new static structural analysis file. Don't be strange. For the fatigue analysis, the static structural analysis is the first step. Right-click on the static structural, pick on Rename. Enter the name as Fatigue Analysis. Enter. Pick on the unit system at the left top corner. Ensure that the unit is set to the mass in tons, dimensions in millimeter, time in seconds, force in newtons, that is metric system. Pick on the engineering data of the project C. Right-click, press hold, pick on Edit. This will open the properties of the structural steel. Structural steel is the default inbuilt material in ANSYS. Under the properties, let us browse to the alternating stress, mean stress data. We can find that a tabular data which represents the number of cycles and the corresponding stress value. Let us change the unit to MPa. The representation of the graph which is corresponding to this data can be changed for its interpolation from log-log to semi-log. This is a normal SN curve which we can find. As we can start reducing the stress level, the number of cycles will go on increasing. Having understood about the property of the structural steel, let us go back to the project page. Pick on the project here. As the structural steel member is defined, the right tick mark represents the material definition is complete. Pick on the geometry. There is a question mark, which means the geometry is not yet loaded. Right-click, press hold, pick on Import Geometry. Since this model already existing in the recent list, let me use the file from here, or else we can browse to our local drives. Pick on the fatigue analysis.stp. The right tick mark just beside the geometry represents the geometry is being loaded. Pick on the model. Right-click, press hold, pick on Edit. Left bottom corner, starting mechanical. This will load the model and attach the CAD geometry to the mechanical, wherein we proceed with the analysis of this part. This is the CAD geometry with sufficient fillets provided to avoid the sharp corners, which leads to the stress concentration. Let us set the isometric view orientation from here. Shift, press hold, middle mouse button, press hold and move the mouse to zoom the part. Press hold Control and press hold middle mouse button and move the mouse to pan the geometry. Pick on the geometry and expand the geometry. Fatigue analysis is name of the solid body and is assigned with the structural steel. The mesh is not yet generated. Right click on the mesh, insert, pick on sizing. Under the geometry selection, pick. Ensure that the body is selected from the selection filter and select this body. The body is now highlighted in the green color. Pick on Apply. We can observe that the body sizing for one body is being defined under the mesh. The body sizing, let us enter the element size 3 mm, enter. Right click on the mesh, pick on Generate Mesh. Observe the model carefully that the elements are properly capturing the geometry. Once it is ensured, let us count what is the number of nodes in this FE model. Check for the statistics. Browse here, almost 40,000 nodes in this model. Let us define the loads as well as the boundary conditions. Right click on the static structural, insert, pick on Fixed Support. Ensure that the fixed support need to be given for the two hole locations, top and bottom. Zoom that area, select those two surfaces. Similarly, select the surfaces from the bottom by pressing hold Control. Pick on Apply. Ensure that under Geometry, 4 faces are selected. Right click on the static structural, insert, say here Apply Force. Where the force need to be applied, the force need to be applied on the surface geometry. Ensure that the surface is highlighted in the selection filter. Select the inner faces of the circular hole. Pick on Apply. The force need to be defined with respect to the coordinate system called as components, that is y component minus 200 force. This force is a static force which we will be converting it into the cyclic load in future. Right click on the solution, pick on Solve. This will take a couple of minutes time to solve the problem. The solution is now complete. Pick on the solution, right click, insert, pick on the stress, equivalent von Mises stress. Right click on this, evaluate all the results. We can observe that there is 110 MPa stress which is coming at this intersection of the lateral arm and the rib intersection. Now let us proceed for the fatigue analysis. Right click on the solution. Insert, pick on the fatigue, that is fatigue tool. Let us observe the details of the fatigue tool by extending this table. Now, the fatigue strength factor, this is default equal to 1, which means there is no surface flaws, surface imperfections, cracks which exist on the surface of the geometry or the model or the member. How is the loading? The loading is fully reversed, which means we can observe that the constant amplitude load fully reversed, which means the actual applied force is 200 Newton. That will be in the positive side as well as the negative side. That's the reason the alternating levels are varying from -1 to +1. This type can be changed from fully to zero based, which means there will not be reverse loading. It will be loaded and removed, still loaded, removed, again loaded and removed. Or it can be a ratio, or it can be a history data. Let us make use of fully reversed loading. The scale factor for fully reversed will be 1:1 by default. We can again play with this factor. The analysis type is stress life, not the strain life. We are interested in identifying the complete life, that is including the crack initiation as well as the crack life. The mean stress theory, let us choose a Goodman theory. There are 4 different theories which are defined. The first one is the default stress strain none. Second is Goodman. Third is Soderberg. And fourth is Gerber. The stress component of interest on which we are going to conclude the fatigue life, that stress component is equivalent von Mises stress. The life units, either we can evaluate number of cycles, number of minutes, seconds, hours and days, or blocks. Let us consider cycles. Right click on the fatigue tool, insert, pick on life. Let us evaluate the life of this part. Right click on the fatigue tool, insert, pick on the damage. Right click on the fatigue tool, insert, pick on the safety factor. Right click on the fatigue tool, insert, pick on biaxiality indication. Right click on the fatigue tool, insert, pick on the fatigue sensitivity. Fatigue sensitivity for life. When we change the load to 50%, what happens? When we increase the loads to 150%, what is going to happen? Totally 25 points need to be plotted on that sensitivity graph. Right click on the fatigue tool, evaluate all the results. The results are evaluated. Let us pick on the first result, that is life. From the details of the life, it is a clear indication that minimum number of cycles that this body can survive is 2.47 e raised to 5, which means the localized area is going to fail before it reaches the infinite cycles, which means a localized stress concentration, which happens because of the fatigue loading. And the remaining part will not experience much of the failure and is capable of handling the cycles till 10 raised to 6. Pick on the damage. It is showing the damage is 1000 highlighted in blue and 4045 for that localized area. About the damage we have discussed at the beginning of the class. Pick on the safety factor. The safety factor evaluated is 0.78 and is maximum of 15. Biaxiality indications. This is the counterplot of the biaxiality indication. Then comes the fatigue sensitivity. The fatigue sensitivity graph explains that currently we have the number of cycles that is, let us pick on the life over here. It is showing 2.47 e raised to 5 that this portion can survive. And when we see a fatigue sensitivity, our loading is 200 MPa, 200 newtons, for which 2.5 e raised to 5 cycles will be survived. If we increase the load to 1.25 times, then the life will still be reduced. If we reduce the life to if we reduce the loading to 0.75 times, then the life may reach to 10 raised to 6 cycles. This is the output of this fatigue sensitivity. Thank you for watching this video. For any queries related to this tutorial, please contact engineeringtutorsdesk@gmail.com or ping on engineeringtutorsdesk on Skype. Visit the Google page for the more video tutorials.